A wind turbine is composed of a number of different systems using different technologies. These systems have to work together. If we wait until we build hardware prototypes to test for integration issues, the errors that we find will be very expensive to fix. We need to have ways of testing for system integration issues before building hardware prototypes. To show you how this can be done, we're going to do this in the Simulink environment. We're going to integrate the different systems together looking for integration issues. We'll see that we're going to replace ideal actuators with more realistic actuators in order to see what the performance of those systems would be and how they interact with one another. We'll also see that we will gradually include more and more systems to test overall system performance. I'll now switch over to the model to show you how this works, how we can gradually include all of these different systems into a single simulation environment. So here's the model that we've been working with. We previously performed an ideal pitch test, where we used ideal actuators to determine the force and speed necessary for the actuator in this system. Now what we'll do is we'll include a hydraulic actuator. So this is a more detailed design of the hydraulic system. The actuation system for a hydraulic actuator, as you would expect, includes things like hydraulic cylinders, valves, orifices, accumulators, and so on. We can now use this more detailed model of the actuator to test system performance. Once we're happy with how this actuation system performs, we can then test the yaw system. So what I'm going to do is I'm going to lock this system and then bring in the yaw system. At the moment, you can see we've been testing the pitch system. The yaw system has been ignored. So now what we're going to do is we're going to include a servo motor yaw system where we have electrical motors that act to turn the nacelle. Now if I go into the subsystem, we have the mechanical system, which includes the yaw ring and the yaw gears. And then we have here the 4 servo motors that are used to rotate the nacelle. Here we see an electrical circuit that has the electrical source and a description of the a model of the motor, the servo motor. And if we go to the next subsystem, we can see the planetary gear models that are used to increase the torque of the motor. So now at this point we've included the yaw system. We could run tests here to see how the yaw system performs. When we're happy with that system, we could then include the hydraulic system that we've been working with to see if these two systems would have any integration issues. It may be that oscillations in the pitch system excite oscillations in the yaw system. This is an integration test we would want to perform in simulation before doing it on hardware. Once we're happy with how these two systems integrate, we can then move further down the line. We can then unlock the hub, allowing the hub to rotate, and then include the gear train. At the moment, as you can see, all of the tests we've run so far, we've neglected the gear train. We can now switch subsystems here and incorporate the gear train into the system, where we have planetary gears and other gears to increase the speed of the shaft that will go into the generator. Once we're happy with how these systems integrate, we can then move on to the electrical system. If I go into the generator subsystem, I can see that at the moment I'm only modeling the mechanical loads. But again, I want to test to see if oscillations in this part of the system will excite harmonics in the electrical system. I need to bring that system into my overall model. So now when I go into the subsystem, I see that I have modeled the electrical system. I have an asynchronous machine that is generating power. That electrical connection to the grid is modeled here, where we have switches that enable it to connect or disconnect from the grid, the transformer to change the voltage, and then the 3-phase connections that go down to the grid. So you can see that we've now gradually incorporated all of these systems into our model. If I go back up to the top level, we can also include aerodynamic effects. So what I'm going to do now is include a Simulink model that takes the wind speed, direction, pitch of the blades, and so on to figure out what the loading on the blades is. And you can see we've used Simulink to do this and incorporated different measurement data that has been used to determine what the lift and drag coefficients would be. Now, if you want a more detailed model of the aerodynamics, you may choose to program that in embedded MATLAB. So what I'm going to do now is substitute in a segmented model of the aerodynamic loads that has been programmed in embedded MATLAB. So we've used a text-based language in order to determine what the loads on the blades would be. So now the next level of system that we may want to look at is the supervisory control. So what I'm going to do is I'm going to include the supervisory control system, which has been modeled in Stateflow. So here you can see we have a state machine that describes the supervisory logic for the wind turbine. This is a very simplified version of that logic, but it is to give you an idea of how we could define this logic. The different states of the turbine are shown by these different symbols: park, startup, generating, and break. And we can see that these transitions describe when we would transition, or when the wind turbine would transition from one state to another. Inside we see the different outputs, again determining whether or not certain systems should be turned on or turned off. So this shows you how we could gradually integrate these different systems all into a single simulation environment to check for integration issues even before we have hardware prototypes.